Okay, thank you. Thank you, Yale, for inviting me before you go to the men's room. I feel like a bit of an imposter here because I never knew Stamatis. I met him once when he worked at IBM, so it's quite a while back. And he was very much engaged in out-of-order processes and the design of high-performance cores for IBM in those days. So I don't have any interesting anecdotes to tell you. This talk is will be brief, and I'm just going to make a very simple observation about machine learning processes that I suspect many of you have already noticed. So we started to see the emergence of these pieces of hardware that speed up neural nets. And perhaps the prime example is Google's Tensor processor. And my point is that they're DSP chips in disguise. Why is that important? So, last bullet. I'm taking neural nets as proxies for machine learning at this point. I realize that's a great big approximation because these things are just classifiers. They don't do deduction or anything else that you find in general machine learning, but they are the area where you've seen hardware support. So that's the point that I'm getting at. So why is this important? It is because in every cell tower around here, there are tons of DSP chips. DSP chips are all over the place. They just don't show up in academia, or at least in the computer hardware community. They certainly do in signal processing, obviously. And we've sort of got a blind spot to those, but they are exactly the kind of machine, well, not exactly, but somewhat close to what you'd want for this kind of computation. So let's just take a look at DSPs. You could sort of time that beginning with the Texas Instrument 3200 series back in the early 80s. There were things before that. There was bit slice chips from AMD and so on. But the main thing that they had is they had basically a Harvard architecture because they needed to get data in quickly. So they couldn't clog the pins up with instructions and data, so they'd separate them. So they sort of rediscovered this idea. And they had a fast multiply and accumulate. And that's really the big deal about these chips in those days. And this is, they did 16-bit arithmetic. This is a little system that you typically see them in. If you looked at the early microprocessors and the early DSP chips, they diverged for a number of reasons, mostly due to cost and resources. Remember, things were in 3 micron was a feature size in those days. And the multiply add was put in the DSPs because it was so central to what they did. It was not, you never found multiplies in the early microprocessors. They just didn't have the space for them. So the DSPs said, we're going to put them in at all costs. Microprocessors say we didn't need them. And they had big, wide bandwidth connections. They had 3 data ports because this is what they did. The kernel of most signal processing algorithms is an inner product. And you want 2 streams in and 1 stream out. And so they used that. Maybe they'd multiplex one of these with the output, but they used a lot of pins. This is before you could put caches on a chip, remember. And in many cases, caches aren't all that helpful for a system that does this. So that was a divergence and sort of brought about the idea of a DSP chip, and Texas Instruments made a career out of it until very recently. And they were considered a different space, principally because of this operation. that they did as one instruction. The divergence extended to early supercomputers. I never quite understood that. This is the block diagram that I'm sure you're all familiar with in Cray 1. There's the vector unit up here, and you stream, this is the 2 in and 1 out of the vector unit up there. It's basically doing this. But it's not accumulating. It's just doing an element-wise vector operation, either add, as I've shown here, 2 in, 2 out, or a multiply, or what have you. But there was no reduction operation to accumulate, which was weird. And I never quite understood why they never did that in the early Crays. I guess they just didn't think about it, or Cray didn't think about it. By the way, the HEP processor, the early CDC had the HEP processor right here, and it was designed by Seymour Cray in the I.O. thing. Who was it? Who put that up? Well, yeah. That's where Burton got it from, actually. Oh, going the wrong way. But going backwards. So what they did in those early machines, you saw this, they did a matrix multiply by doing an outer product instead of the normal inner product, because it preserves vectors. You end up with a 3D thing that you finally you have to squash all those planes together, add them all together. So you do need to use the scalar unit for that, but it kept, by doing this outer product, you keep the vectorization going as much as possible. But it's very costly in terms of memory bandwidth. In those days, that didn't seem to be a problem. Much higher bandwidth of the cache-based solution. Less data reuse. You only touch each element once, which is interesting. Going back to Walid's talk, if you're doing sparse operations, you will probably want to do outer products, because capturing the next data item in a sparse structure requires you to do several operations just to fetch the data. So why not use it when you've got it, but only use it once? You can do that with an outer product. After a while, the new supercomputer, if you like, which is a GPU, I guess, or many GPUs actually, started to include the Mac unit. And that wasn't until 2010. I think Fermi, correct me if I'm wrong, but I think Fermi was the first GPU to actually have it. It wasn't an ASIC GPU. And it's amazing how long that took, how these two fields of computing, the signal processing people and the high-performance linear algebra scientific / graphics people, didn't get into a simple, well-known operation called dot product. So what does that have to, where does that come together? Well, diagrams that you've seen a million times, the famous neural net, and the operation on this thing is really, in drawing this diagram, it's just vector matrix multiply. With a little difference, which is why I put that strange operation in there. It's a non-linear operation. It's a thresholding on that dot product, basically. So deep neural nets, they just have many layers, and the weights of which, as you know very well, are created during the training phase. So this set of operations here, so this is the basic algorithm. The weights correspond to the number of weight matrices correspond to the depth, right? And the other fact is, which is annoying, is that because we have this nonlinear operation, we cannot pre-multiply all the matrices, which means we have to reevaluate them in inference every time, because the input will change based on, or the output, I should say, for different inputs will change based on that nonlinear operation, unfortunately. Otherwise, neural nets would be easy to do. You could just pre-multiply all those matrices together, which just represent the bipartite graphs of each layer, right? And you just evaluate it once, and you'd be done. But what this thing gives you is classification surfaces that are nonlinear, because it is a nonlinear operation. That sort of shows you can get very complicated ones. So these neural net machines are simply classifiers. They're not brains or anything else like people try to say. They're just simple classifiers. What's made them so successful is that they've been trained, they're very large, they've been trained with massive amounts of data, like Facebook's deep face or something like that, where they've got so much data to feed into this thing that they actually start to show performance on a par with a human being doing classification. So you've got things like a deep face, for instance, is better than humans at recognizing faces. But these are not intelligent in the sense that they don't do deduction, they don't do any of those kinds of things that we think about as being. In a sense, they're complicated enough, and maybe someone will do this one of these days, they're complicated enough that I think they actually enumerate all possibilities in some indirect way. So this operation, to get down to the one point I want to make in this brief talk, is that this operation, which is central to DSPs, is also central to these new brand of machines typified by the Google TPU. So why aren't we using all these DSPs out there? That's an interesting point. And why aren't the people that are building cell phone towers not buying, or, to turn it on its head, buying TPUs from Google? Well, that's a bit of a rhetorical question because they're not for sale, but you know what I mean. So, in other words, the key ingredient's been around for eons, this DSP map, right? So if you look at all the companies in that space, they suddenly have a deep neural network solution, magically. And if you look at, you've got, let's skip this one, SIVA, which is a signal processing company that builds a DSP chip, relatively successful company, has now got a chip that uses DNNs to do vision. Vision classification, not vision understanding. NVIDIA claim they have a TPU-like processor that they're going to announce very soon. And that's beyond the Volta. We know that Google have recently talked about their old TPU, which is actually a tensor processing unit. So they're not satisfied with vector multiply, they're calling them tensors. But none of them are tensors. I get they're trivially tensors because they are actually vectors, but the classic sales job. The point is that if you saw that recent paper that they broadcast everywhere, that's a 2-year-old design that you're looking at there. And it's quite successful. And they claim it beats out Microsoft's GPU solution and NVIDIA's GPU. Microsoft's FPGA solution, the Catapult approach, and NVIDIA's GPU. Who else is doing it? Well, Intel went crazy and purchased Nirvana, which is another sort of deep learning machine. But I don't have a lot of data on that. That's not widely known. Another desperate attempt by Intel to be relevant. I'm not putting my money on this ever working. GraphCore, which is a small startup in the UK, does their own intelligent processor unit. I think somebody just bought, and was it Qualcomm, I think, and many others. This list could go on. It's not a new thing, let's put it that way. You can see the EE Times, just grabbed a couple of headings. EE Times is where I get all my technical information these days. You can see that everybody's jumping on the bandwagon. So there's two kinds of approaches that people notice this convergence that I'm talking about, and they've said, hey, we can repurpose our signal processing chip because it can do in our products really efficiently and maybe modify it by putting a thresholding function on it so it does a nonlinear operation, or we can start from scratch. Google did that and wowed everybody at ISCA recently. And this is their machine. I mean, it's just basically a bunch of matrix multiplies, 64,000 MAC units. And it circles the data from the MAC units around back. So this is a layer of the neural net just going around this thing. And what they did is they used 8-bit arithmetic, because that's the precision that they need in it. It means that they can put this blob here in a relatively small space. So they learned something that the DSP people had known a long while, which is you can use limited precision integer fixed point to do a lot of things, because a lot of things in signal processing are lost. I mean, in your cell phone, the signals coming in there, they start the processing off with 2 and 4 bits, so that you don't even need 8. So these guys have been doing approximate computing for many, many years. So everybody else is saying, oh, let's have 8-bit fixed point to save space and area, etc. Anyway, the nice thing that Google does is that, of course, they created this TensorFlow environment, so you can actually play around with this machine. I think it's this machine, maybe the newer one, or it may be a fake one, in this age of fake things. But you can develop your neural net very quickly. They've got a nice interface there, so it's an interesting thing to play around with if you want to do that. So there was a sort of shootout between NVIDIA's K80 and Google's TPU, and this is the stuff they published in that paper that I'm sure many of you have downloaded and read. If you actually look at if you compare it to a new GPU, it doesn't look so good. So there was a little bit of bogus representation in that paper, in my opinion. So if they'd have actually compared it to something close to that, and they compared it to a very old NVIDIA product, if they'd have compared it to something newer, they would have seen that they don't do so well. But it's half a dozen of one and 6 of the other. They do the same kind of things. And where we're going is that there's been an intense investment in these tensor processing units. And I pick on Google because they're the most forthcoming about details. But their latest one, which is the one they use now, actually supports floating point, because they've gone through the same cycle. The DSP people realized that if you've got fixed point, you've got to understand the algorithm very well. You have to understand rounding, you have to understand overflow, and so on. With floating point, a lot of that's automatically taken care of at great cost, but it makes it easier for the programmer. Making it easier for the programmer is always the cost-effective way to go, because that's the manpower that you're spending your money on. So they've suddenly amped up to floating point arithmetic, which is sort of what the DSP people discovered after that. So they've gone through that space fast, easy program. There's not much details. I think it was used in that recent Go player. That Go player, by the way, was not just a classification system. There was a lot more to it than that. So it's interesting to see how quickly that space has evolved. So you've got a convergence of two things. So the question is, the companies that build DSPs for a living, are they going to be out of business because companies like Google and related companies that are building what I claim is a very similar kind of processor can just do their job? We'll find out, I guess. So that's the conclusion. There's a lot of activity in this space. which is why we're seeing hardware, Nirvana, GraphCore, Google, etc. Is fueled by pragmatism. There's been an unreasonable success with these classifiers. They've become very successful, and I claim because the data's the neural network or the perceptron-based classification has been around since I was an undergraduate, which is a long while ago. Vacuum tubes were a big deal then. And they never really did much because the machines that they were running them on were so small and the data sets were so small. But now you've got these farms of literally tens of thousands of machines that can do a very highly parallelizable activity, and they've got massive data sets because we put pictures of our faces on Facebook and so forth. And so there's no clear boundaries now. And it will be interesting to see, I'm not prognosticating what's going to happen, it'll be interesting to see if these two rivers of separate computer architecture philosophies will combine, or which one will sort of repurpose itself, or maybe there will be a bit of both. I don't know. Anyway, that's my talk. Thank you for listening.
Thank you, Trevor.